Now I'm going to give you some other definitions for matrix vector and vector matrix multiplication. The dot product definition of matrix vector multiplication is this. The product m times u is the R vector v such that entry R of v is the dot product of row R of m with the vector u. So to calculate the matrix vector product using this rule, we would take the dot product of the row 1, 2 with this vector, the dot product of row 3, 4 with this vector, and the dot product of row 10, 0 with this vector. And those dot products are the values of the entries of the resulting vector. Here's a simple example, downsampling. So perhaps I have a large, high-resolution image, and in order to put it on a website, I want to downsample. I want to get a lower resolution image. Here's how I do that. Each pixel of the low-res image corresponds to a little grid of pixels of the high-res image. And it's the intensity value of the pixel in the low-res image is computed as the average of all those little pixels in that grid. Now, averaging can be expressed as a dot product. We want to compute a dot product for each of the low-res image's pixels. That's a lot of dot products. But we can express all these dot products as a single matrix vector multiplication. Here's another example, blurring. To blur a face, we replace each pixel in the region we want to blur with an average of pixels in the neighborhood. Again, average can be expressed as dot product. So using the dot product definition of matrix vector multiplication, we can express this image transformation as a matrix vector product. Gaussian blur works the same way. You're computing a sort of weighted average, but that can also be expressed as a dot product. Here's another application. Earlier we talked about searching for a short audio clip within a longer audio segment. These audio clips were recorded digitally, so they really consist of numbers arranged in a sequence. And we saw that the way to seek a short clip in a longer audio segment is to carry out a whole bunch of dot products, one for each of the possible positions of the short clip within the longer audio segment. Lots of dot products, but we can represent all those dot products as a single matrix vector product. Recall the sensor node problem. We wanted to know how much current is consumed by each hardware device on the sensor node. So we used test periods, a series of test periods. In each one, we measure the total power consumed during that period. And for each test period, we have a vector that represents how long each hardware component is on during that test period. So we have a bunch of those vectors. And now we want to use all these measurements to calculate the energy consumed per second, that is the current draw, for each hardware component. We can formulate this as a system of linear equations. We solve for x to find out for each hardware component how much current it draws. So here's a system of linear equations. Each equation specifies the value of a dot product of a known vector with our unknown vector x. We take those vectors a1 through am and put them in a matrix. And now we can express all these dot products as a single matrix vector equation. So again, the problem of computing the solution to a matrix vector equation is a fundamental computational problem. Let's see how to formulate the sensor node problem as a matrix vector problem. Remember, our goal is to compute the current draw for each of the hardware components in our sensor node. We define the domain to the radio sensor, memory, and CPU. Those are the hardware components. And our goal is to compute a vector U that maps each hardware component to the current drawn. To do that, we establish 4 test periods. For each of those test periods, we'll measure the total power used during that test period, and we'll put those measurements in a vector B. In addition, for each test period, we have a vector duration that specifies for each hardware component how long that hardware component is on during that test period. To find this vector U, we solve the matrix vector equation A times X equals B, where A is the matrix whose rows are these duration vectors. Let's solve this matrix vector equation using the solve procedure. First, we have to construct these vectors. They all have the same domain. Now we construct them using that domain. Next, we construct this matrix whose rows are the vectors. We'll use rho-dict Chemat for that. Let's see how that matrix looks. Next, I'll construct this vector B that gives for each test period the total milliamp per seconds consumed in that test period. Now we're ready to use the solve procedure to solve this matrix vector equation. We'll assign the result to the variable rate. And now let's look at the entries of rate. To check that we've really gotten a solution to the equation, we'll compute the residual and compute its dot product with itself. That number is plenty small, convincing us that we do have an accurate solution to the matrix vector equation. Keep in mind 2 things though. One, it's not necessarily the only solution. We haven't shown that there's a unique solution. And 2, even the values in the vector rate are only represented approximately due to the limitations of floats. You'll recall we studied triangular linear systems that look like this, with zeros down here. And these correspond in a natural way to triangular matrix vector equations. And so we'd call a matrix of this form a triangular matrix. Here's the formal definition. We can use backward substitution to solve a matrix vector equation like this one. Triangular matrices will be very important later on. You'll be writing code to do matrix vector multiplication and vector matrix multiplication. Now you could use either of the definitions I've given, the dot product definition or the linear combinations definition. And you'll do that in homework. But using those definitions, it's not easy to exploit sparsity in the matrix. So we'll look at another definition, one I call the ordinary definition of matrix vector multiplication. Entry R of the resulting vector V is the sum over all the column labels of MRC times entry C of U. This formulation makes it easier to write code to compute the matrix vector product. So here's the obvious way you'd write it. You'd iterate over all the entries in big R, the row labels, and compute the value of the corresponding entry of the product as the sum. This still doesn't exploit sparsity in the matrix. So we can use another idea. We initialize the output vector V to the 0 vector, and then we iterate over all the non-zero entries of the matrix and adding terms as according to the definition. So here's pseudocode for that process. Now I'll present some very fundamental algebraic properties of matrix vector multiplication. For any vector V and any scalar alpha, the matrix A times alpha times V is the same as alpha times the matrix A times V. And for any vectors U and V, A times the sum of U and V is the sum of A times U and A times V. Let's go through the proof. To prove A times alpha v equals alpha times AV, we just have to show that corresponding entries of the left and right-hand sides are equal. That is, that entry I of A times alpha v equals entry I of alpha times A times v. Well, let's write A in terms of its rows, A1 through AM. Now, by the dot product definition of matrix vector multiplication, entry I of A times alpha v is the dot product of row I, AI, with alpha v. And that's equal to alpha times the dot product of AI with v by the homogeneity of dot product. On the other hand, by the definition of scalar vector multiplication, entry I of alpha times the vector A times v is alpha times entry I of A times v. And by the dot product definition of matrix vector multiplication, entry I of A times v is row I, AI, dotted with v. So we've shown that corresponding entries are equal. Similarly, we can show that A times the sum of u and v equals the sum of A times u and A times v. We show that corresponding entries are equal. So we need to show that entry I of A times u plus v equals entry I of A times u plus A times v. So again, we use the representation of A in terms of its rows. By the dot product definition of matrix vector multiplication, entry I of A times u plus v is the dot product of row I, namely AI, with u plus v. And this is equal to AI times u plus AI times v by the distributive property of dot product. On the other hand, by the dot product definition of matrix vector multiplication, entry I of A times u is the dot product of row I, AI, with u. Entry I of A times v is the dot product of row I, AI, with v. And putting these together, entry I of the sum, A times u plus A times v, is AI dotted with u plus AI dotted with v. So we've shown that corresponding entries are equal. And that completes the proof.